Assalamualaikum and very good day. We are from Group 6. We present our project based on dataset named House Price Advanced Regression Techniques from Kaggle. The objective is to simplify the dataset and finding the average house price. The dataset has 81 variables describing houses in Ames, Iowa. We have identification of the house, sales price, which is the target variable, numeric features such as lot size, categorical features such as house styles, and ordinal features such as quality of material. Why the data set suitable? First, the high dimensionality. Second, mixed data types with continuous, categorical, and ordinal features. Third, highly variable scales. And fourth, it has noises. Overview of the stages. First, data understanding. We are going to explore structure, types, missing values, and distributions. Then data transformation to normalize numeric variables, discretize continuous variables, and smooth noisy features. Last one is data reduction by applying sampling, reduce size and dimensionality, but retaining key info.
In this presentation, I will show three techniques: min-max normalization, z-score normalization, lot transformation by using sales price and lot area from the house price dataset. So first is the min-max normalization. It's actually rescale the data so that all the values fall between 0 and 1. Okay. This is done by subtracting the minimum values and divided by the range as per week 4 lecture note. On the left, you can see the original distribution of sale price and the lot area. On the right, after min-max normalization, the values are compressed into the range from 0 to 1. This technique is useful when we want bounded values for algorithm like K-means clustering. Next is z-score normalization. Is actually standardize the data by centering it around the mean and scaling it by the standard deviation. This means the transform data has a mean of 0 and standard deviation of 1. In this histogram plot, the original distribution are shown alongside the z-score version. This method is helpful when we want to compare how far each value is from the average, and it is commonly used in the statistical analysis. Okay. Finally, is lot transformation. Is usually applied to reduce the skewness in the data. Housing price and lot area often have a long tail with extreme values. By applying the algorithm, we compress those large value and make the distribution more balanced. In the plot, you can see how the lot transformation pull the long tail and reveal a clearer pattern. Okay, so in summary, min-max normalization rescale values to a fixed range, z-score normalization standardize value around the mean, and lot transformation reduce the skewness.
For discretization, I apply two different techniques to transform the continuous variable lot area into categorical bins. First, I extract the lot area values into a variable x from the data frame. The first method is equal width binning. Here, I use the cut function to split the entire range of lot area into 4 intervals of equal size. This means the numerical distance between bin edge is the same for all bins. I then assign each observation to one of these 4 bins, creating a new categorical variable, lot area underscore EQW. The second method is equal frequency binning, sometimes called quintile binning. Instead of dividing by equal numerical width, this method divides the data based on quintiles, specifically quartiles in this case. I calculate the quartiles, which split the data set into 4 groups, each containing approximately 25% of the observation. I remove any duplicate breakpoints to ensure valid bins, and again use cut function to assign each observation to a bin, creating lot area underscore EQF. To visualize the difference, I generate 3 side-by-side plots. The left plot is histogram of the original lot area. As you can see, the distribution is highly right-skewed, with most properties having small to moderate lot size, but a few having very large lot. The middle plot shows equal width discretization, where the entire range of lot area is divided into 4 bins of identical numerical width. Because lot area is so skewed, almost all properties fall into the first bin, while the other 3 bins contain very few or even zero observation. This method is simple and works well when the data are uniformly distributed, but it performs poorly when the variable is skewed because it creates unbalanced and sometimes empty bin. On the right plot, we have equal frequency discretization. Here, the data are divided so that each bin contains approximately the same number of observations. You can see that all 4 bins have very similar heights, meaning the distribution of value is balanced across categories. This makes equal frequency binning especially useful when the dataset is skewed or when we need balanced bins. In summary, equal width is easy to interpret and works well with evenly distributed data, but it fails with skewness. Equal frequency handles skewed data effectively and produces balanced category, making it the most suitable method for variable like lot area.
Let's begin with the raw data. Here we plot the sale price of home against the year they were built. At first glance, there's a general upward direction where newer home tends to cost more. But what really stands out is the noise, which means the variance is extremely high. Homes built in the same year like 1980 can sell anywhere from just above 100,000 to beyond 300,000. With this much scatter, any true trend is hidden behind individual differences like renovations, location, factors, and unusual property conditions. So to uncover the underlying pattern, we apply smoothing. So here in the after view, the black dot is still representing the individual homes, but the colored line represent a smooth estimate of the trend. So by reducing the high frequency noise, the overall pattern becomes a clear and non-linear upward trend with price increasing more sharply after the 1980s and especially after in 2000s. So smoothing is particularly useful in two situations where when points fluctuate heavily at the local level as seen in 1980s cluster, so smoothing stabilizes the view. And when we want to see the long-term structure instead of a random fluctuation. In short, smoothing helps us focus on the general rule rather than the exceptions. So here we apply a two-smoothing method where the red line is lowest, a locally weighted regression technique, allows build small regression model across a local neighborhood of the data. Because it adapts to local pattern, it captures a complex nonlinear relationship, which make it suitable for real estate trends that don't follow a straight line. And the blue line is the normal kernel smoother, which use a Gaussian weighting to average nearby points. And it's excellent for reducing a noise while preserving the general shape of the data. So both smoothing method reveal the same overall long-term pattern where home price rise over time, with a stronger growth after the 1980s. However, in this plot, the normal kernel show more fluctuation in early years due to sparse data, while lowest produce a smoother and more stable trend. And this indicates that lowest is a more robust when the data distribution is uneven. And in conclusion, smoothing transforms a noisy scatter plot into a clear and interpretable insight, which is a newer homes consistently command higher price, and that rate of increase has accelerated over time. Thank you.
Hello everyone, my name is Sophia Anissa binti Jairi. Today I will demonstrate two data reduction techniques, which is numerosity reduction and dimensionality reduction using PCA. This method helps simplify large dataset while retaining important information. First, let's look at numerosity reduction. This method reduces the number of rows in a dataset. I apply random sampling both with and without replacement, taking 50 rows from the original dataset. Then I perform stratified sampling, taking 10% of the data from each neighborhood. Finally, I use aggregation grouping data by neighborhood to compute the average sales price and count. This reduces the dataset drastically, but all individual level details are lost. Next, we move to dimensionality reduction using principal component analysis or PCA. PCA reduces the number of columns or features while keeping most of the data variance. For PCA, isolate 7 numeric variables from the dataset. First, I replace missing values with the median and then I center the data so each variable has a mean of 0 before performing PCA. Then, I computed the covariance matrix and perform eigen decomposition to find the eigenvectors and eigenvalues. Multiplying the center data by the eigenvector gives the principal component score, which are uncorrelated new variables. I also computed the variance explains and cumulative variance. Then I created a variance table showing how much variance each principal component explained. The top 3 principal components capture most of the variance, around 80 to 90%, meaning we can represent the dataset in 3 dimensions instead of 7 by retaining the main patterns. This plot shows how much variance each principal component explains. I keep the top 3 principal components capture most of the variance. Even though we reduce from 7 variables to 3, the main pattern and structure of the data are preserved. Here are samples of the top 3 principal components for the first few rows. In summary, comparing the two methods, numeracy reduction reduces the number of rows, making computation faster by losing individual level data, while PCA reduces the number of features, keeping most variance, but the new variables are a combination of the originals and harder to interpret. In practice, both methods can be combined for a very large dataset that reduce row first and reduce dimension. As for the case to balancing data reduction with information preservation. Thank you.
Now the summary part. First, the data preparation. We have variable types identified as numerical and categorical features. Then we do explore some data distributions, and also we clean missing values using appropriate strategies like using median imputation. Then we do the normalization by using 3 approaches. First is minimum and maximum scaling by rescaling the data. Then Z-score standardization. It is based on mean and standard deviation. And the last one is log transformation by reducing the skewness and stabilizes variance. Next is discretization. We're using 2 approaches. The first one is equal width binning, that divides numerical range into uniform intervals, and equal frequency binning that divides the dataset into same number of cases for each bin. Then we go for smoothing using 2 smoothing methods. The first is LOAS that adapts locally and captures nonlinear patterns. And the second one is normal kernel smoothing that provides a globally smooth trend based on weighted averages. The last one is data reduction that we're using 2 approaches. The first is numerosity reduction that have random sampling, stratified sampling, aggregation, and then the dimensionality reduction that using PCA that reduces correlated variables. Here is the final dataset dimension, which shows average sales price of the house based on neighborhood, which consists of 25 neighborhoods and numbers of houses in each neighborhood. The key achievements, we have a refined dataset that showing average sales price based on neighborhood, and then we have reduced dataset size while preserving major patterns and variance, and also significantly reducing dataset dimensionality from 81 to 3, and we reduce random noise via smoothing. The challenges encounter, first we have missing data, and then we encounter it through selective imputation, then highly skewed distributions, we encounter through normalization. The mixed data types, we separate pre-processing for each type and proper handling before PCA. The high dimensionality, the PCA removed and condensed correlated features into relevant one. And the last one is noise through smoothing method. Thank you.